Ionic Metallic Bonding. As we learned in the periodic table, valence electrons is the number of electrons in the outermost shell of the atom. In here we can see the example of the halogens, where fluorine, chlorine, bromine, and iodine at the right hand side has 7 electrons in the valence shell. Alkali, alkaline, boron, carbon, nitrogen, oxygen families, halogens, and noble gases are considered representative families. In general, the number of valence electrons of a representative element is equal to the group number. Now it's time to learn about the octet rule. For this, let's get back to the noble gases. They are usually unreactive in chemical reactions, and the reason for this is that they are stable at having 8 valence electrons, except from helium, which has only 2. The noble gases, as you can see, is helium, neon, argon, krypton, xenon, and radon. Gilbert Lewis found in 1916 that in forming compounds, all atoms tend to achieve the electron configuration of noble gases, which have 8 valence electrons, calling this the octet rule. As a consequence, metals tend to lose their valence electrons, obtaining a complete octet in the next energy level, becoming cations or positive charge ions. In the example, we can see magnesium that has 2 electrons in the valence shell. By losing these 2 electrons, the next energy level has 8, so magnesium becomes stable with a charge of positive 2. On the other hand, nonmetals tend to gain electrons in their valence shell, obtaining a complete octet and becoming anions, or negative charge ions. In the example, we can see fluorine that is unstable because it's missing 1 electron, and by gaining it, it achieves the octet in getting a charge of negative 1. Summing up, a neutral atom can either lose or gain electrons to attain their octet in their valence shell. Ionic bonding is the complete transfer of valence electrons between atoms. It is a type of chemical bond that generates 2 charged ions in ionic bonds. The metal loses electrons to become a positively charged cation, whereas the nonmetal accepts those electrons to become a negatively charged anion. In the example, we can see lithium in the left as the cation, the giver, and fluorine, the anion, as the receiver. Ionic bonds require an electron donor, metal, and an electron acceptor, non-metal. In the example in the left, we can see sodium as the metal and chlorine as the non-metal. This causes a difference in charges between sodium and chlorine, positive and negative, and that makes one of the strongest forces of attraction between atoms, that is the electrostatic force. Now let's take a look at the properties of ionic compounds. Ionic compounds are crystalline solid at room temperature. Ionic compounds generally have high melting points. Ionic compounds form crystal shapes composed of 3-dimensional patterns. These patterns consist of atoms or groups of atoms in order and symmetrical arrangements which are repeated at regular intervals, keeping the same orientation to one another. This is called crystal lattice. Ionic compounds can conduct electricity when melted or dissolved in water. Now, let's talk about alloys or metallic bonds. Alloys are metallic materials consisting of 2 or more elements in which at least One is a metal combined in such a way that they cannot be readily separated by physical means. The physical and chemical properties of an alloy can be modified by heat treatment and mechanical working. In most cases, the alloy is chemically more stable than the component elements, so that alloys are designed for a specific resistance to actions such as corrosion, wear, fatigue, and temperature. Other alloys are made to impact magnetic or electrical properties, strength, formability, etc. Thank you for watching.